In Part 2 of Session 1, we will cover crude oil composition, exploration, transportation, and an overview of refinery processing.
There are many important events in the history of crude oil, and I have selected only a few. In my view, major price changes are also key historical events because they are strongly influenced by geopolitics, wars, pandemics, and global economic crises. You will see this clearly near the end of the timeline. In the 1850s, the first commercial oil operations began in Russia, Romania, and the United States using simple batch distillation. The first successful commercial oil well was drilled in 1859 in Pennsylvania, and this discovery encouraged investors to build small, simple refineries close to the oil fields on the U.S. East Coast. In many cases, coal distillation facilities were adapted for oil processing, an early milestone in the modern oil industry. As demand increased, batch distillation could not keep up. Russia introduced the first continuous distillation, a major turning point for the industry. Soon after, the first vacuum distillation units in the United States opened a new era because lubricating oils could now be produced from crude oil. Later, adding steam to vacuum distillation, first developed in Russia, further improved the yield and quality of lubricant oils. Thermal cracking was another key step. It allowed refineries to convert low-demand heavy materials into more valuable fuels, increasing profitability. Wartime demand for kerosene and gasoline accelerated innovation, and by the late 1930s, catalytic cracking was introduced, converting heavy fractions into high-octane gasoline, which was in very high demand. In the late 1940s, platinum catalysts were introduced, transforming gasoline production by improving octane number and yield, and by generating high-purity hydrogen as a valuable byproduct, hydrogen that is essential for many modern refinery processes. A major price shock occurred during the 1973 oil crisis. In response to geopolitical conflict, an embargo restricted oil shipments to several countries, including the United States, creating a significant market disruption. Prices increased from about $3 to $12 per barrel, and the market never returned to the earlier price level. The embargo was lifted in 1974, but the structural impact on oil markets remained. The second major oil price shock occurred during the Iranian Revolution and the subsequent Iran-Iraq War, when crude oil prices rose from about $14 per barrel to roughly $35 per barrel. The most recent price shock is also the most familiar. During the 2019 to 2020 COVID-19 pandemic, industrial activity declined sharply, global demand dropped, and WTI crude experienced extremely low prices, around $20 per barrel in 2020. For perspective, oil prices had reached about $140 per barrel in 2008, before the market decline associated with the global financial crisis.
Let us return to crude oil. Crude oil is a complex mixture of thousands of hydrocarbons, and almost every hydrocarbon family can be found in it. One major category is paraffins, which can be straight chain or branched. Olefins also exist, although paraffins are generally more dominant. Another important family is naphthenes, which are saturated ring structures. These can be precursors to aromatic hydrocarbons, which contain benzene rings. Crude oil also contains compounds that include sulfur, nitrogen, and oxygen in their molecular structures. These impurities must be reduced in final products, especially sulfur compounds, because of environmental and product quality requirements. In some crude oils, trace heavy metals may also be present and must be managed. In summary, crude oil contains many hydrocarbon families mixed together. Nature combines them. The refinery's job is to separate and convert them into useful products for daily life. Now let us look at the big picture of how refineries separate crude oil into product groups. Refinery products can be grouped into four major categories, from low to high molecular weight. 1. Petroleum gases. 2. Light distillates. 3. Middle distillates. And 4. Heavy ends. Heavy ends are often divided into heavy fuel oils and specialty products. Middle distillates are commonly divided into kerosene and light fuel oils. Light distillates include naphtha and gasolines, and petroleum gases can be grouped as natural gas and liquefied petroleum gases, or LPG. Methane and ethane are typically part of the natural gas group and are often consumed within the refinery as fuel for process heaters. Propane and butane are commonly sold as LPG, a cleaner burning fuel used in applications such as barbecue tanks. Straight-run naphtha is often split into light and heavy naphtha. These are important feeds for petrochemical complexes, and they can also feed catalytic reforming to produce higher-quality gasoline components. A familiar example is mineral spirits, also called white spirits, which are blends of light and heavy naphtha adjusted to meet flashpoint specifications and widely used as paint thinners. In the middle distillate range, kerosene and jet fuels are key products, along with diesel fuels in the light fuel oil subcategory. At airports, the smell of unburned or partially burned kerosene-type fuels can sometimes be noticed during boarding operations. In the heavy range, heavy fuel oils are used for industrial energy and marine bunker fuel. Finally, specialty products include lube oils, waxes, bitumen, and carbon black, familiar in everyday life as motor oil, candles, pavements, and pigments.
You might be interested to know how crude oil is formed. A widely accepted theory of crude oil formation involves the decomposition of marine organisms under high pressure and temperature over geological time. Organic material accumulated on ocean floors and became buried under layers of silt, mud, and fine sand. Over millions of years, increasing pressure and temperature transformed this organic-rich layer into hydrocarbons. Sediments hardened into shale and sandstone, which can act as porous reservoirs, while shells and skeletal material often formed limestone. This diagram shows a typical oil field structure: natural gas at the top, oil in the reservoir zone, and saltwater below. The reservoir can be trapped by geological structures such as a salt dome. A well is drilled into the reservoir, and if the reservoir pressure is sufficient, oil can flow naturally to the surface. For high-viscosity crude oils, steam may be injected to reduce viscosity and improve flow. In other cases, gas injection is used to increase reservoir pressure. Once produced, crude oil is transported, often by pipeline, to processing facilities. Pipelines are generally the most economical method for transporting crude oil. However, leaks can cause serious environmental damage. This is one reason pipeline development can become controversial, including disputes within Canada. For example, Alberta seeks access to coastal export terminals to reach Asian markets, while British Columbia has raised environmental concerns that have delayed some pipeline projects. With that context, let us assume the crude oil has reached the refinery after a formation process that took millions of years. A refinery can be viewed as having three major processing categories. 1. Physical separation, primarily distillation. In lube oil production, extraction is also commonly used. 2. Chemical conversion and treating, to change molecular structures into more valuable or cleaner forms. For example, sulfur atoms must be removed from sulfur-containing molecules using reactors and catalysts under controlled conditions. Hydrotreating removes sulfur, nitrogen, and oxygen compounds. Catalytic reforming increases aromatic content and improves gasoline quality. Cracking processes convert heavy hydrocarbons into lighter, higher-value products. 3. Blending, mixing intermediate streams to meet product specifications based on market demand, customer requirements, and regulatory standards. Looking again at all units in the crude oil refinery, by combining the hydro-treating sections and focusing only on the units responsible for treatment and purification while removing unnecessary connecting lines, the diagram becomes much simpler and easier to follow. The first category is physical separation. The main unit operations in this category are distillation, including atmospheric distillation, vacuum distillation, and light ends and gas separation. Extraction, including solvent deasphalting, solvent extraction, and solvent dewaxing. In addition, the desalter can be considered as a separate step because it uses an electrostatic field to separate salty water from crude oil.
The next category includes units where molecular structure is changed.
Polymerization, isomerization, alkylation, and catalytic reforming modify hydrocarbon structures to improve product value and quality. Hydrotreatment removes sulfur, nitrogen, and oxygen from hydrocarbons, converting them mainly to hydrogen sulfide, ammonia, and water. These polar compounds are then separated from the hydrocarbon products. Another major category is cracking, where large molecules are converted to smaller ones. This can occur by thermal processes such as coking and visbreaking, by catalytic cracking, or by catalytic cracking in the presence of hydrogen, commonly called hydrocracking. The final category is blending, which takes place in the blending and tank farm systems. A network of tanks, pipes, pumps, valves, and instrumentation allows operators to mix streams and adjust final product specifications before shipment to the market. To emphasize the structure, let us review the units once more. Crude distillation separates crude oil into gases, naphtha, kerosene, gas oil, and atmospheric residue. The crude desalter removes salts and water. Vacuum distillation separates heavier fractions from atmospheric residue. Hydrotreating of naphtha, kerosene, and gas oil removes sulfur, nitrogen, and oxygen compounds. The catalytic reformer upgrades naphtha into high-octane gasoline components. Gas treatment and separation purify LPG and fuel gas and remove hydrogen sulfide. Finally, catalytic cracking converts vacuum gas oil and sometimes heavier feeds into lighter products such as gases, gasoline, kerosene-range material, and gas oil. Viscobreaking applies mild thermal cracking to reduce the viscosity of heavy fuel oils. Hydrocracking converts vacuum gas oils and heavy residues to lighter products, gases, naphtha, kerosene, and gas oil, using hydrogen and catalysts at high pressure and temperature. Coking uses severe thermal cracking to convert heavy feeds into lighter products and solid coke. De-asphalting separates asphaltic material from vacuum residue, producing de-asphalted oil and asphalt. Alkylation transfers alkyl groups to produce higher octane blending components. Polymerization combines light olefins to produce higher molecular weight hydrocarbons. Isomerization converts normal paraffins to isoparaffins. An aromatics plant uses solvent extraction to separate BTX, benzene, toluene, and xylene from reformate. A lubricating oil plant uses extraction and de-waxing processes to produce lube base oils. Bitumen blowing oxidizes vacuum residue to produce bitumen grates. Sulfur recovery converts collected hydrogen sulfide into elemental sulfur. The hydrogen plant supplies hydrogen to the refinery. Steam reforming and the water-gas shift reaction are the key steps, using steam and light hydrocarbons to produce hydrogen. There are additional units in a refinery as well, and I encourage you to identify and study them as we progress. Thank you very much for watching Part 2 of Session 1. Please continue with Part 3 of Session 1, where we will briefly discuss petrochemical products derived from the hydrocarbons obtained from crude oil.